Alright, in this video we're going to solve a programming problem, and we're going to use Jupyter Notebooks, probably use the MATLAB IDE too, and we'll do it in MATLAB and we will do it in Python as well. So you can see I've got a notebook here. This is a MATLAB notebook. I've got another one open here that's a Python 3 notebook. So let's start with the MATLAB notebook, and I want to. This is a MATLAB interpreter here, right? So it's going to give me an output. Notice the star. That means that it's thinking, and when you do the first command, it usually takes a little bit longer. I think it has to initiate the MATLAB engine before you get an output, but we'll get an output shortly here, and then there we go, and then subsequent outputs won't take as long. And to make it give me an output, I'm pressing Shift Enter. Right? If I just push Enter, I'll just get a new line. Okay, so let's delete some of these. So if I have the cell selected and I just press DD, it'll delete that cell for me. So pressing escape puts me in this command mode, and then once I have that cell, DD deletes it. Okay, so we're going to start over with a clean notebook. And what I want to do now, notice here it says code, but I have other options here. I'm going to go to a heading and get rid of that, and let's type the name of the problem that we're going to solve, so we can see the problem. So the problem that we're going to work on now is one where we have a list of numbers, and another number. Let's call it K. And what we want to know, we want our function to return a Boolean true if any two numbers in the list add to the number K. Okay, so that's going to be our problem. And now I want to go back to coding. Get rid of this one. Okay. All right. So there's a few ways that we can do this. We're going to start with the most basic way, and then we're going to move on to some more advanced ways. We'll move on to different things that we can do with data structures in Python to solve this as well. And let's start out with something fairly simple. So let's make a list of numbers, and in some programming languages, a list is a formal data structure, but in MATLAB, we're just going to use a vector. There are differences. We'll talk about those maybe a little bit in this video and in future discussions. But for now, we're going to create a vector. I'm going to call that vector li. And I'm just going to put a few numbers in it. Okay, so here we have just a MATLAB array with 4 numbers in it, 10, 15, 3, and 7. And let's, assuming that we're not always going to use a vector with 4 numbers in it, let's let this variable len equal the length of that vector. So length is a MATLAB built-in command, so that will give us the length. And let's also set this variable output to 0. So this is going to be the Boolean that we will turn to 1 or true if we find that 2 numbers add up to our number K. And we need to define K as well. That's going to be the number that we're looking to see if we can sum up to. And in this case, let's let it equal 20 so that we can we'll have success, right? No, we won't. Let's let it equal 10. Let's see. Let's let it equal 18. So that way 15 and 3 is 18. So we should get a true output here. Okay. So there's a couple ways we could think about doing this. For this first go around, we can add 10 and 15, and then we can add 10 and 3, and then we can add 10 and 7, and then we've added 10 to all the numbers, and then we can move over to 15, and we can add 15 and 3, 15 and 7, and then we've added 15 to all the numbers, and then we can move over and add 3 and 7, right? So we can kind of iterate over the vector that way. And to do that, I'm going to use a nested for loop. So my outer loop I'll call T, and that is going to range from 1. Remember that in MATLAB we're starting with our indices start at 1, and we want to go to the length, the end of the vector, so we're going to go from 1 to n. And now I'm going to have an inner loop, which I'll call S. Now S is going to control this. The T is going to control the first number that we add, and then S is going to control the second number that we add. So we want to start with the first number, but we're going to add the first number to the second number. So, but when we're starting with the second number, we want to add the second number to the third number. So that's we're always going to start with the one that is next to the first number. If the first number is 10, we're going to start with 15. If the first number is 15, we're going to start with 3. So that means that we need to put T plus 1 here, and that's going to go to the end of the vector as well. And now we're looking to check and see what the sum is. So if Li of T plus Li of S, so I'm adding those two numbers together, equals K, then we will change the number output to 1. And now I can end my if statement, and I can end my first for loop, and I can end my second for loop, and now I will just print out the output. Okay, one thing to mention, this double equal sign here. Double equal sign is testing if two things are equal. So this if statement, if this number plus this number equals K, this expression, since I'm using a double equal sign, will either evaluate to true or to false. If Li of T plus Li of S does equal K, this will evaluate to true. And if it does not, then this will evaluate to false or 0. True is 1, false is 0. And so when I'm using the if statement, remember that if I'm using the if statement, basically if this evaluates to true, then I execute this piece of code. But if this evaluates to false, I don't execute this code and I skip down and I'll stay in the loop. Okay, so let's run this and see what happens. Okay, so I forgot to suppress this. Here we see that we get an output equal to 1, which is what we expected. Let's just run this again. Okay, so output equals 1. All right, that's what we expected. Let's see if we can do some different things with this. I'm going to keep that up there, but I'm going to paste the code down here, and let's make a few edits. Instead of hard coding my list of numbers, I am going to use the MATLAB command random integer, randi, and let's let K, we'll make K equal a larger number here. And so now let's talk a little bit about what this random integer expression is doing. So I'm just going to take the help here, and I am going to put it into my notebook. Okay, so this is from the MATLAB help. It's creating pseudo-random integers. We call it pseudo-random because it's not truly random. The way that random number generators, the way that pseudo-random number generators work, which is most random number generators in computers are pseudo-random, is you give them a seed, a number that they start with, and they keep iterating off of that seed, and they'll generate a stream of random numbers. In this case, it's going to be random integers. And the thing with a pseudo-random number generator is that if you use the same seed, it will always output the same list of random numbers. So you need to change the seed if you want the random integers to be different. Here it's taking them from a uniform discrete distribution. So what this means is that any number in the distribution is equally likely to be selected. We can see here that if we use this syntax, randi imax kind of n, comma n, it's going to give us an n by n matrix with integer values ranging from 1 to imax. Imax m comma n gives us an m by n matrix of numbers ranging from 1 to imax. And there's a whole bunch more in the help file if you want to look at it. But basically what we're doing here is we are using this to generate random numbers. Okay, so it looks like this is still thinking. Okay, so I had to restart the machine because there was an error in this code and it crashed the computer. So let's just look at what the error was. I'm going to bring the help file back in. Actually, let me not do that for now. So if you recall, we were just a minute ago talking about this random integer command in MATLAB, and I used improper syntax here. So I want the numbers to range from 1 to 10,000, right? These are random integers, and the syntax I'm using here, let me just type it as a commented text. So what we want is L equals random integer, and then we have imax, which is the maximum integer. So the integers will range from 1 to imax. And then if I use just this other 10,000 here, then I'm going to get a 10,000 by 10,000 matrix of random integers, and that's not what I wanted, right? I want just a vector of random integers, and so I got way too many integers here, which is what gave me the problem. So let's make this a little bit smaller and let's use the appropriate syntax. So the syntax that we want here is imax m n, and that what this is going to do is this is going to give us an m by n matrix of random integers, and I want it to be a vector, right? So I want it to be just a row of random integers. So I want one row, and let's go with like 500. So we'll have, in fact, I can just uncomment that, and I'm not even going to comment this out. I'm going to get rid of it because that really caused me problems a minute ago. Okay, let's see. Anything else I want to... let me just talk about this. I was playing around with some different ways to solve this problem before, and I was interested in how long it takes for this part to execute. And so this command, tick, and this command, talk, what happens is this will return the amount of time, right? It's like starting a stopwatch here and turning it off here, and it'll tell me how much time it took for all of this code to execute, which is really the heart of the algorithm, right? That's where I'm integrating, or where I'm iterating over the vector. Okay, so let's give this a shot. And I had to restart, so it should take a minute for the MATLAB engine to boot up. Okay, and I have an error here. Unrecognized variable IMAX, right? Because this should be, let's make this 1000 and try again. Okay, so in this case, we got 1,000 random integers, and we were looking for, so we would definitely always get a 0 here, because we can only go up to, we had 500 integers, we can only go up to 1,000. So this number is way too big, because we're never going to get 2 of them that add up to 18,000. So let's just say 124, and chances are we're going to get a 0 again. Oh, we got a 1 this time. Okay, and let's run it a couple more times. Looks like I'm often getting a 1. Maybe if we make this number smaller. Okay, and that's how we got a 0. So this is, I think, maybe the most basic way that we can solve this problem, where again, what we're doing is we're starting from the first one. We add every other integer to that first one. We check all of those. Then we move over to the second one, and we add every other integer to that second one. And so if you want to think about the way that this problem scales in terms of how long it takes to solve it, or how much more time it takes to solve it as the number of entries in this vector grows, right? That's, we're thinking about what we would call the big O notation of this problem, and solved with this particular algorithm. And so if we think of the number of entries in this vector as some number n, and we think about how many operations we would need to do in order to completely solve the problem, then we would need n squared operations. Okay, n times n. We need n squared operations to add every number to itself, and get all the possible sums of any 2 numbers in this vector. And just to kind of figure this out, if we come down here, let's just make this a markdown. So for the first number, for 1, I would need to do n minus 1 additions. And then for the second one, I would need to do n minus 2. And then n minus 3, etc., etc. And it can be shown that this sequence equals n times n minus 1 over 2. And so we have an n squared term here. So we say, when we do this big O notation, we just take the highest power term. So that's big O of n squared. Right? It doesn't matter that we're dividing it by 2. Basically, this is going to scale like n squared. N squared is the dominant term of this expression. Okay, so that is, I would call this a brute force method of doing this in MATLAB. And the question is, can we do any better? Can we cleverly figure out how to solve this problem and do better than scaling by n squared? So now we've switched over to Python, and I've got this little Python code here, and we're going to see that this does considerably better than the last code that we wrote, where we did a brute force iteration over the vector to solve the problem. So we're solving the same problem here, and I want to talk through the approach, what we're actually doing here, and then we'll walk through this code so you can see how it all works. I think the first thing to describe here is we're using a different data structure here. So in MATLAB we used an array to solve the problem, and here in this Python implementation we're using something called a set. You can see right up front here we're defining scene as a set. A set is different from an array. It is a collection of items. The difference, one of the main fundamental difference with a set, it's unordered, and the objects in the set are unique. So there can be no repeats of the same object in a set. So this is a data type that I don't believe exists natively in MATLAB, but does in Python. Sets are really, the data structure of a set is really the same as the mathematical definition of a set. So if you're familiar with sets or set theory, that's what we're doing here. Now, if we go back to the first line of this code, here, this DEF, this is a keyword in MATLAB that we use to define a function. So we're defining a function. The name of it is toSum, and we're passing two things in, LST, this list LST, and K, which is going to be the number that we want to check if anything in the list adds up to that number K. So that's what the first line is doing here, is just defining a function. Standard Python syntax for doing that. And then, as I said before, the first thing that happens in the function is that we initialize scene as a set. Right now, the set is empty. Notice in this implementation that we are not using a nested loop. We're using a single for loop. Python has a slightly different syntax. For num in list, this means that we're just going to iterate over the list that was passed in. We're going to basically run through that whole list one time. Let's just jump down to this line. This is, so remember, scene is the name of the set that we've defined up here. So this is a set, and there is a method in set called add. So scene.add is calling the set method add num. And so what this is doing is it is taking the number, the current number that we're looking at from the list, and it's adding it to the set. But it will only add it to the set if it doesn't already exist in the set, because again, sets can't have duplicate values. Now, if we look at this line, this is really the clever part that gets us better performance with this code than with the brute force code. If k minus num is in scene, this means if k minus the number is already in the set scene, then we're going to return true. So let's build a list here and kind of walk through it to see why this code works. So suppose, I'm just going to use Markdown here. Suppose our list is 5, 10, 3, and 8. And let's suppose k is 11. Okay, so we're going to have our scene, our set, and we can just begin adding numbers to that. So we're going to iterate over this list for num in list if k minus num is in scene. So we start with the 5. We look at the 5, and k is 11. 11 minus 5 is 6. We look at our set scene. It's not there. So we don't return true. We just add that number. We add the number to scene. So we add a 5. Okay, and then we move over to the 10. So we're back. We're iterating around the loop again. We move over to the 10. K minus num, 11 minus 10, that's 1. Well, I've only got a 5 in here. I don't have a 1. So I just add the 10 to my set. Now I move over to the 3. 11 minus 3 is 8. That is not here, so I put a 3. Finally, I move over to the 8. 11 minus 8 is 3. I look through my set and I see that I do have a 3 here, and so I return true. So in this case, the obviously 8 plus 3 is 11, so this would come back true. So as this list gets longer, we just have to do one more operation every time we add one more thing to this set, right? Basically, we have to do one more subtraction. So this iterating over this list and doing this part of the code scales by n if there's n items in the list. And then you might say, well, what about when we're checking to see if that number is in the set, and what about adding things to the set? What is the complexity there, the computational complexity there? So to understand why that part, the complexity of that part, adding items into the set and checking to see if items are already in the set, has a complexity of 1. In other words, it doesn't matter how many things are in the set. Checking to see if something is in the set is always the same in terms of computational hardness. In order to understand that, you have to understand something called a hash table. So let's talk about that a little bit, because really that'll help you to understand why we're using, another reason why we're using this set data structure here. So to understand the way that a hash table works, which is what the underlying data structure of the set. Let's use an example. So suppose all these people are students at a university, and there obviously could be many, many more. And suppose we had a function called a hash that takes the letters of their name, we convert it to ASCII or whatever, and maps it to a unique number. So Jill uniquely maps to 11, Naomi uniquely maps to 2, etc. So in other words, if I take Jill and pass Jill into the function, the output will be 11. And if I pass Naomi into the function, the output would be 2. Okay, now it would be beneficial if the outputs were always unique, but the nature of a hash function is that it can take virtually any size input, but it gives you a fixed size output. So for example, you might be able to take any reasonably sized input and passes out, say, 128 bits. So clearly, if you're passing in inputs that are more than 128 bits, you're going to have two things that have to map to the same thing, and that's called a collision. There's ways to deal with that, but for now, for our purposes, let's just assume that we're always going to get a unique output. So no one besides Jill is going to have the output of 11, no one besides Fred is going to have a 9, etc., etc. Okay, then what we can do is we can create this table based on the hash. So here we see that we have the same names, but now they are in locations based on what their hash value was. So now imagine this table is much, much larger, and I want to find Steve. Well, if I just search through the table, on average, I'm going to have to search through half of the table to find any given person. Sometimes they might be the first person on the list, sometimes they might be the last person on the list, but on average, I'm going to have to search half of the entries in the table in order to find any single person. However, with this structure, I know I'm looking for Steve. I run the hash function on Steve and get the output 4, and I know to look directly in memory location or table location 4 to get Steve. And there could be something, there could be additional information here, like, Steve's grades, the courses that he's enrolled in, all the different data about Steve as a student at the university, not just his name, right, because I've already got his name. But I can put information about Steve here. So then, whenever I want to look up information on a student, instead of having to search through all the students on the list, I just run this hash function, and that tells me exactly where to look. So if we go back to the code for a moment, this line of code right here, where we do k minus num, and then we check to see if it is in the set seen, occurs very quickly, because all I have to do is run the hash on this value and then look at that location in scene and see if it's there. And the real point here is that this operation is completely independent of how many items I have in the list. I can make the list as long as I want, and this will always run in the same amount of time, or what we call constant time. So the difference between this code is that what dominates the time that this code takes is running through the list one time, so that I need to do n things because the list is n long, as opposed to my MATLAB code over here, where I'm really running through the list twice, or really more than twice, right? Because when I'm using this implementation, I do the 1, I have to do all of these items, and then when I do the 2, I'm looking at all of these items again. So really, this is, if you think of that, the amount of operations that causes, that's where I get to this n squared. You might ask, can we do even better than n, O of n? And the answer is we could. I'm not going to go through that code here because it's a little more complicated than I want to show just yet. But what we could do is we could sort the list, the original list that we get, this list, we could sort that, and then we could run a binary search on k minus each item in the list. And running a binary search on n elements takes n log n, O of n log n, which is better than O of n. So we could do slightly better. But this implementation is good. It's running in O of n is is good. It's very, very fast. Okay, so just to recap, we defined this problem given a list of numbers and a number k, return whether any two numbers in that list add up to the number k. We started out with a brute force where we look at every possible sum and just check to see, is that sum the one I'm looking for? And then we did then we figured out that that has a computational complexity of n squared. And then we looked at a better implementation where we're exploiting the data structure, the set data structure in Python, and we're kind of using this clever idea where if k is the number that I'm checking to see if they sum up to, and I subtract the number that I'm looking at from k, and if that's not in this set already, I write the number num to the set, and continue to iterate through. That's kind of the clever thing that you can do to make it so that you only have to iterate through the list one time. I think the important thing to think about here is that the nested loop structure in general, when we're iterating over lists or arrays, the nested loop structure is in general going to give us this n squared. And if you can find ways to do what you want to do where you're only iterating over the list or the array one time, in general, that's going to be faster code.